Have you ever stopped to watch a sunset on Earth? The sky bursts into a magnificent painting of fiery reds, warm oranges, and soft pinks. It's a familiar and comforting sight, a signal that the day is ending. Now I want you to imagine something quite different. Picture yourself standing on the surface of another planet. You are on Mars, the red planet. The sun, a small distant disk in the sky, begins to dip below the horizon. But instead of the familiar warm colors, the sky around the sun starts to glow with a cool, eerie, and beautiful blue. It's a truly alien sight, isn't it? This isn't science fiction. It is a real phenomenon, captured by our robotic explorers millions of miles from home. This strange blue glow raises a wonderful question. Why? Why would a sunset on Mars be blue when ours is so spectacularly red? To understand a blue sunset on Mars, we first need to think about color itself. Color is not something that objects have. Instead, it is all about light. The light from our sun, which we see as white or yellowish, is actually a mixture of all the colors of the rainbow. Think of it like a packet of sweets with every flavor mixed together. When this sunlight travels through space, all those colors travel together in a straight line. But when that light hits something, like the air in a planet's atmosphere, things get interesting. On Earth, our atmosphere is relatively thick and made up of tiny gas molecules. These molecules are very good at scattering blue light. This is why our daytime sky looks blue. Let's compare our two worlds side by side. Earth is often called the blue marble. It is wrapped in a thick, protective blanket of air, rich in nitrogen and oxygen. This atmosphere gives us our blue skies, our breathable air, and our dramatic, fiery sunsets. It is a dynamic and life-sustaining feature of our home planet. Mars, on the other hand, is the red planet. Its atmosphere is incredibly thin, less than 1% of the density of Earth's. It is mostly carbon dioxide with no significant amount of nitrogen or oxygen to speak of. Standing on Mars would feel almost like being in a vacuum. This dust is the crucial difference. The Martian atmosphere is not just thin, it is dusty. The air is filled with tiny particles of iron oxide, essentially rust, which gives the planet its signature red hue. These dust particles are much larger than the gas molecules in Earth's atmosphere, and because of their size, they interact with sunlight in a completely different way. Before we launch ourselves across the vastness of space to Mars, let's take a moment right here. Let's stand on our own world and watch the day come to a close. The sunset on Earth is a daily masterpiece, a spectacle of color that has inspired artists and poets for millennia. As the sun begins its slow descent towards the horizon, the sky transforms. During the middle of the day, when the sun is high overhead, its light takes a relatively short path through this atmospheric ocean to reach our eyes. The tiny air molecules are the perfect size to intercept and scatter the shorter wavelengths of light, which are the blues and violets. But as the sun gets lower in the sky, the situation changes dramatically. The sunlight no longer takes a direct short path. Instead, it has to travel sideways through much more of the atmosphere to reach you. Let's dive a little deeper into this journey of light. We can think of sunlight as a stream of tiny packets of energy called photons, each corresponding to a different color. When they leave the sun, they are on a straight path through the vacuum of space. For 8 minutes they travel unimpeded, but then they encounter the very edge of Earth's atmosphere. The moment they enter our air, they begin to collide with the gas molecules that make it up. It is a cosmic game of pinball, and the outcome determines the color of our sky. During this long journey, most of the blue light is scattered away from our line of sight long before it reaches us. What's left over? The light with the longer wavelengths, the reds, oranges, and pinks. Now let us leave the familiar blue and red skies of Earth behind. Our journey takes us millions of miles across the cold vacuum of space. We are arriving at Mars. As we descend through its atmosphere, the first thing we would notice is how different the sky looks, even in the middle of the day. There is no rich, vibrant blue greeting us. Instead, the sky is a pale, washed-out color. It is a strange pinkish tan or butterscotch hue that stretches from horizon to horizon. This is our first clue that the rules of the sky are different here. The real artist of the Martian sky is dust. The air on Mars is permanently filled with incredibly fine particles of dust. These particles are kicked up from the planet's rusty surface by global winds and can hang in the atmosphere for weeks or months. Imagine the scene in Mission Control at NASA's Jet Propulsion Laboratory on July 20th, 1976. Humanity had just successfully landed its first spacecraft on Mars, the Viking 1 lander. Its mission was to study the Martian environment, search for signs of life, and be our first stationary eyes on this alien world. The scientists were eager to look up. They programmed the lander's camera to capture the moment the sun dipped below the horizon. What the scientists saw was astonishing, and at first a little confusing. The sky around the setting sun was not red or orange. Instead, it showed a distinct, beautiful blue glow. This was the first time humans had ever witnessed a sunset from the surface of another world, and it was the opposite of what they might have expected. The red planet, it turned out, had blue sunsets. Now we arrive at the very heart of the mystery, the scientific principle that unlocks the secret of the blue Martian sunset. While our earthly skies are governed by Rayleigh scattering, Mars has its own master artist. This process is called Mie scattering. This type of scattering happens when the particles doing the scattering are roughly the same size as the wavelength of light itself. On Mars, the fine dust particles suspended in the thin atmosphere are just the right size for this to occur. Unlike Rayleigh scattering, which throws blue light around in every direction, Mie scattering is much more directional. It tends to scatter light forward, in the same direction that the light was already traveling. Think of it like this. If Rayleigh scattering is like a firework exploding in all directions, Mie scattering is more like a focused beam from a torch. The dust particles catch the sunlight and redirect it, but mostly in a forward cone. Let's use an analogy to picture what's happening. Imagine you are standing in a large, dark room filled with a very fine mist. Now, someone at the other end of the room shines 2 torches at you. During the Martian day, it is as if both torches are on and pointed right at your face. The bright glare is overwhelming, but the whole room is filled with a faint red glow from that wide, diffuse red beam. This is the reddish Martian daytime sky. Now, the sun begins to set. As the bright, direct glare of the torches disappears below the wall, something amazing happens. The wide red glow that filled the room begins to fade, as its source is now blocked. But the narrow, intense blue beam is still traveling over the top of the wall. For a moment, you are looking directly into this focused beam of blue light. The rest of the room is growing dark, but this brilliant blue searchlight is aimed right at your eyes. This is the Martian sunset. Thanks to our robotic explorers, we do not have to imagine these sunsets. We can see them. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have acted as our eyes on Mars for years. The images sent back by these rovers are simply spectacular. They captured the Martian sunsets with a clarity and color fidelity that was previously unimaginable. The ghostly blue glow seen by Viking was now rendered in stunning detail. The mission team would often command the rovers to take a series of images, creating time-lapse movies of the entire sunset sequence. For the first time, we could watch the blue aureole brighten, peak, and then slowly fade into the Martian night. These beautiful images were also a goldmine of scientific data. By measuring the brightness of the blue glow and comparing it to other colors, they could precisely calculate the size of the dust particles responsible for the scattering. And so, our cosmic detective story comes to a close. We began with a simple, almost childlike question: why are sunsets on Mars blue? We journeyed from the familiar fiery skies of Earth to the alien twilight of another world. The solution, we discovered, was not magic, but a beautiful and elegant piece of physics. It is a tale of light, dust, and the fundamental rules that govern our universe. Why do mysteries like this matter? In the grand scheme of things, the color of a sunset on another planet might seem like a trivial detail. And yet, the quest to understand phenomena like the blue Martian sunset is fundamental to who we are as a species. It is driven by the same innate curiosity that led our ancestors to look up at the stars and wonder what they were. It is this desire to explore, to understand, and to see what lies over the next horizon that has propelled all our greatest discoveries. So, let us continue to ask these questions. Let's continue to send our robotic explorers out into the solar system to be our eyes and ears. Let us marvel at the strange beauty of a blue sunset on Mars, because in every one of these cosmic mysteries lies an opportunity for discovery. Each puzzle we solve, no matter how distant, expands our understanding of the universe and our place within it. It reaffirms the most powerful and enduring human trait of all, our unending universal curiosity.